Yeah, good morning. We will start our fifth lecture of our course, Vehicle Dynamics, today. So in this course, in the last class, we were looking at importantly how this physical concept or physics of the simple harmonic motion and the corresponding equation go hand in hand. So they are blended together. So if you say that you know vibration, it is not that you explain only the physical motion. It is also important that you explain the motion through mathematics. That's what we are trying to make an attempt to learn. And in that process, in the last class, we were trying to represent to understand better the phase angle between rotating vectors of a simple harmonic motion, right? So for that purpose, we were taking an exponential function as a trial solution, and we are trying to work on it. And we had some kind of not having a clarity of while plotting that there are doubts arised, and then I was trying to clarify the doubts. So my lecture today would start from clarifying that point, and then we will go ahead adding more and more understanding of our basics of mechanical vibration. And also that what we have seen in the last class is importantly what is called a beat phenomena. So that's where you could differentiate addition of two vectors which are having same frequency called a synchronous vector is different than that of looking at beat phenomena. So beat phenomena happens when you add two vectors, rotating vectors, which are differ by its frequency of excitation, the frequency of motion. Slightly. So that's what is creating your beat phenomena, where in beat phenomena you see that there will be the variation as function of the amplitude keeps on decreasing from maximum to zero and again at times maximum and comes. So you could see that the variation of amplitude again there in this beat phenomena. And then importantly, we have looked at two important scales, the decibel scales for sound pressure and acceleration. And also we just learned what is the definition of octave. So this is what is essentially in the last class that we were looking at it. And today's class, I'm going to just to give a clarity of what we were doing in the last class and continue. And then you will know at the end what is the purpose of this class. The main purpose of this particular fifth lecture is to understand state space representation of your harmonic motion, right? Yeah. So let me share my screen. Hope all of you are able to see the screen.
Yes, sir.
Look at that. In the last class, we were just looking at this and we had some difficulty here. So first of all, let me do these corrections in this. One is that this T I was writing here, please remove that. That's already there in that. Right? And then importantly, you had a doubt of plotting these graphs. So the plot of this graph, both real and imaginary, this blend in it. Of course, if you look at the real part of this trial function as solution, you have displacement given by a cos omega t and velocity given by a omega cos omega t plus pi by 2 and acceleration given by a omega squared cos of angle pi omega t plus 5. So if I plot this, if you have to plot this, then it starts from here. See, this is for kind of guidelines only, this angle. So it's 0, pi by 2, pi, 3 pi by 2, 2 pi, and then you'll have here 5 pi by 2. And so on, it goes like that, right? So this scale, horizontal scale, is to account the angular displacement of these rotating vectors. So you can pick any point according to this motion. So the curves what are drawn represent these harmonic functions clearly. But the start of point, if you have to see in omega t is 0, that starts from here. That doesn't matter. So from omega pi by 2 to 5 pi by 2 is one cycle, or it is 0 to 2 pi one cycle. So I can extend this curve on left side as well as on the right sides. So it is that at what particular angular displacement you look at the motion. So if I look at this particular motion, and this what this corresponds to this, like that you can go where this is, instead of writing it pi by 2, I will write 0 here and so on. So that's to be understood. Also, you can see that yesterday there was a question that can we have an imaginary part of this also? Yes, that is also represented by the same variation of velocity, acceleration, and displacement on this graph. So what does that is you can represent it like this. So you know that the same displacement, velocity, acceleration can be written as function of imaginary part of this solution. So if that is so, displacement is a sine omega t. So when you put omega t 0 angle, that is going to be 0. That is this point. So maybe whatever is plotted yesterday is for imaginary part explicitly appearing here. If you have to account this real part, you have to shift your vertical axis to this point and see. So this can be, this vertical axis can be moved here and there, but the same curves can represent both the real part as well as an imaginary part from which point you look at it. So is that clear? Yeah.
Yes, sir.
And then another doubt, it's not a doubt, I just overlooked while doing in the lecture number 3, writing what is this series for cos theta. So cos theta also would have one minus. This is not plus, it is minus. And this is not plus minus. So this minus become plus here is because I theta, when I multiply with I, then it is I theta whole squared is going to be minus. So please do that correction. So this series 4, equation 4, cos theta also is 1 minus theta squared by 2 factorial minus theta per 4 by 4 factorial, where sine theta would all from here, theta minus theta cube by 3 factorial and so on. So these two are substituted in this, would give this. So this is a other correction. Otherwise, whatever that we have been discussing so far, all are absolutely fine, correct, and you should not get confusion, especially on this. Yesterday, of course, the doubt would come. I could have projected straight away to you the plot and then explain, that may not be retained in your mind. So as we are learning, we should try to attempt to do plot, and that time we may make a mistake or fumble all, but that would tune us to have a clarity of our understanding. So that's the reason why I was making an attempt to do it on, and today I just have clarified on the yesterday's doubt as well as the question arised, can imaginary part be representing this curve? So obviously both of them are represented. It's all at what angular displacement we look at your rotating vectors, right? So with that note, let me start today's class. And today's class is lecture number 5. Someone please mute your, that is 11/8/2021. See someone audio, there is kind of disturbance, so mute all. If you have to talk, you can unmute and speak. Let's go ahead with this. Right. So today I'm going to look at again the solution of this simple harmonic motion, so that you will understand something working principle of a harmonic oscillator. So for that I'm going to represent now my trial solution as a function of a Laplace variable, right? So what is that we are doing is undamped free vibration. So if we see that the harmonic motion, whatever that we study, is called undamped free vibration because we do not consider any damping. So main important assumption here is our spring mass system, what is considered at its static equilibrium position, is simply would execute the motion where the degree of freedom is only going up and down. So it's single degree of freedom system, and it is called an undamped free vibration because no resistance to the motion, no resistance to the motion. And most importantly, the system is conservative system because there is no resistance, there is no energy dissipation. So energy dissipation to have, we need to include an element called a damper. or a damping, and that is not included in this. We will be looking at our mechanical vibration with the consideration of damping also that we will see in the next class. And today's class, since this model, what we have been learning so far, does not include any damping element because of an important assumption, no resistance to motion. And it is going to have a motion, oscillatory motion only in vertical direction. So it is single degree freedom motion, and it is function of x, function of 1 degree freedom, or that's any time the position describes the motion, right? Now, in this, we have looked at the representation of solution by a vector. We looked at as a complex number. Now I'm going to represent my trial solution x of t as c e raised to st. So where here s is called Laplace variable. See, ultimately in vehicle dynamics, what are that you are going to study is not only the response study, also the stability analysis of your vehicle. So when you have to do a stability analysis of vehicle, it is always convenient that you represent your governing equation of your motion in a state space form. And you would see that the characteristic equation of your physical phenomena is represented by a polynomial of variable representing polynomial is a Laplace variable. So that's why it is very important class that this fundamental that you are clear with. So S is Laplace variable. So here now, if I differentiate this, what is S? S, of course, is going to have some real part plus imaginary part, right? So earlier we had here it's a e raised to omega t, only imaginary part I have taken and then we were doing. Now if I replace this with this, then I would have accordingly my equation, and that also can be a solution for your undamped free harmonic oscillation. And taking this particular solution would bring in a physical device called harmonic exciter. Right. So let's take that now for this. What is its velocity? That is x dot of t. That is going to be c. C is what is the constant, arbitrary constant that can be found out through its initial conditions. Like in this case, we have been so far seeing the motion can be executed to have its free oscillation or natural vibration, either by giving initial displacement or initial velocity. So from that's what we have seen, or you can also give both of them. That's a generic case we have been discussing. So now if I get my velocity vector, response here is that the first time derivative of this function, that's going to be c s e raised to st, and that's going to be s x of t. And then x double dot of t would be going to be c s squared e raised to st, and that's going to be s squared into x of t. And now you know the governing equation for this is mx double dot plus cx dot, that's equal to 0. So with the considering x of t is not equal to 0, I can have the substitution of this into this equation. So if I substitute these two in this equation 1, which is my governing equation, I would have now that would be replaced by c into m s squared plus k into e raised to st, and that's going to be 0. So c e raised to st is x of t. So x of t cannot be equal to 0. So I can make m s squared plus k equals 0. And this s square can be obtained now minus k by m. That's going to be under root of, that's going to give me s is going to be plus or minus under root of minus k by m. That's going to be plus or minus under root of, not under root of, plus or minus omega nt. Omega n. So under root of k by m is what is omega n we have seen, right? So this is what is now roots of this characteristic equation. So what is this I have written here is what is called a characteristic equation. Characteristic equation. So the roots of this characteristic equation would give me now the solution. So I have two roots S1 and S2. S1 and S2, that's going to be plus omega n. So this is I times because it's minus inside. So this is omega n I. So it's going to be plus I omega and minus I omega. It's going to be plus I omega n and minus I omega n. So I have, these are my roots. So this is, so what is my general solution? The general solution can be now expressed as x of t as C1 e raised to 1 of this S1t. So that's going to be I omega n t plus C2 e raised to minus I omega n t. So this is going to be my general solution. So we were knowing that in the last class we represented e raised to I plus or minus I theta, right, as cos theta plus or minus I sin theta, right? You know this. So similar way, now I can expand this and then I'll rewrite this as follows. So this x of t equals this. I'm going to rewrite this as this. I'm going to write this one is going to be C1 cos omega nt, C1 cos omega nt plus C1 I sin omega nt. I C1, you can write it like this. Sorry. I C1 sin omega nt plus here this is going to be C2 cos omega nt minus C2 I C2 sin omega nt. Sin omega nt. So now I can group this as real part and imaginary part. So I will have these two there. So C1 plus C2, if I combine together, that would act as a coefficient for cos omega nt. Plus here I have so that's going to be I into C1 minus C2 into sin omega nt.
There's a plus in between.
Where?
Sir, after cos omega nt.
Here.
In the
This
last
one you
line.
say here.
Sir, in the last line.
Here. In the last
Sir,
line, this is plus. Yeah, C1 plus C2 into cos omega nt plus omega nt plus, I'm sorry, that is t, and then plus I into C minus C2 sin omega nt. Good. And this is what is now x of t. I would again see the C1, C2, all are arbitrary constant. These constants can be always found out from the initial conditions, right? And I would combine now the C1 plus C2 as one constant, and that is going to be A1 cos omega nt plus, so this is one function, this is another one. So in between plus sign, you said correctly, yeah. And then this is going to be C1 minus C2, I'm going to write it as A2 into this I also. I'm going to take that as A2. So I'm taking this imaginary I times this, whatever is there, into this as A2 sin omega nt. So now you see this again represented as a vector. You don't see that in explicit appearance of your I there. So that is now into this arbitrary constant, which is a complex number, A2. Now you have, this is your solution. So let's now find out what are my other derivatives. So that velocity is another. So that's going to be x dot of t. It's going to be A1 omega n. So A1 omega n sin omega nt. That's going to be with minus sign plus A2 omega n cos omega nt. And then now, why do I have these two derivatives only? I can also get the third one. I don't do it at the moment because now I can write the initial condition and find out this A1, A2, right? So what is A1, A2? How do I do that? At t is equal to 0, I can have x naught as A1 and x naught dot x x naught as A1, right? T is equal to 0, that is x of t equals 0. I get x naught is equal to A1 and x naught dot as equal to omega n A2. So if I substitute, so I will get from this A1 as x naught and A2 as x naught dot by omega n. So now this constant can be substituted in my solution. I will have that here x of t as A1. In place of A1, I'll have x naught cos omega nt, and in place of A2, I'll have x naught dot omega n sine omega nt. Right? So you have here subscript n for omega. This circular frequency is a special circular frequency called natural frequency, as this equation represents response for undamped free vibration, right? So that you should be always aware of. So this is your response now. So now I can also write in another compact form by introducing a simple trigonometric term. So in this place, I have my A1, A2 from initial condition. So if I introduce A1 as A cos phi and A2 as A sin phi, right? I define this constant A1 as A cos phi, A2 as A sin phi. Then what is my A? A would be under root of A1 squared plus A2 squared, under root of A1 squared plus A2 squared. So by substituting this, I would have cos squared 5 plus sin squared 5, that goes of, so I square on both sides and add and take square root. So trigonometric terms goes off. I can substitute here my values here. That is x naught square plus x naught dot by m whole square is what is my E. So that is amplitude. And I introduce here cos phi. What is this? Phi is phase angle. So phase angle. So I can get this phase angle phi as tan inverse of A2 by A1, A2 by A2 by A1. So that's going to be x naught dot by this is omega n, this is omega n. X naught dot by x naught omega n, x naught omega n. So this is my phase angle. So if I have this and I can substitute now, this function is going to be represented as this x of t is going to be equal to a cos omega nt minus phi. So this response can be represented like this if I define A1 as A cos phi, A2 as A sin phi. That's very simple. In place of x naught, you put A1. See, this is A1, right? And this is A2. So put this. So your response is going to be what? X of t is going to be A1, sorry, A cos phi cos omega nt plus A2, I'm going to substitute this, A sin phi sin omega nt. So now let's call this angle as A and this angle as B. So you have cos A, cos B plus sin A, sin B. That refer to what? Cos A minus B. So that's what is this. So this is A and this is B if I define. I know cos A minus B is what is going to be cos A, cos B plus sin A, sin B. That is how you can write this into this form. So this is most interesting compact form, where it relates three important aspects that I was telling you in the very first lecture. What are those? Amplitude, frequency, and phase angle. So these are three important aspects of your simple harmonic motion or harmonic oscillators. So now you can also have another way. So in some textbook and literature, you would see I can have another way defining like this. So instead of having it A1 as A cos phi, I can take that as A sin phi. So differentiate from that, I take this A naught cos instead of that sin phi naught. Differentiate from this, what is taken, I just take it like that. So A2 equals A naught cos phi naught. So I can take like this also and work out. If I do that, what does that change would be? There is no change in amplitude definition. That's going to be under root of x naught square plus x naught dot by omega n whole square. That's same. But phi naught has to be carefully looked at. It's tan inverse of A1 by A2. Just tan phi naught I needed. So that's A1 by A2. So then it's going to be the other way writing x naught omega n by x naught dot. And if I substitute this similar to this in this function, I would have my expression of x of t is going to be a sine omega n t plus phi naught. So which we have seen in the earlier class. So you can also have either this as your solution or this as your solution or this as your solution, anything. So either cosine or cos function itself is harmonic motion representation. If you want to have both the combination cos and sine, then you should have to go for complex number representation, or like in the case of getting its more characteristic nature and then stability analysis point of view, it is always convenient to represent in a Laplace domain. So we were having now Laplace variable introduced and deduced our solution to this point now, right? So let us continue now looking at important.
Excuse me, sir.
Yeah.
So can you explain how this phi naught came?
Oh, this phi naught came. It's just an assumption. See, I just have here. This is a set of definition or values of A1, A2. A naught sine phi naught I just put. This is, don't understand this, not refer to initial state or something. No, it is only with respect to variables. It's all the constants here, right? So this A naught here and phi naught, I just wanted to differentiate from what I consider in this case. I get to both of them. If I consider A1 as A cos phi or A2 as A sin phi, I get this all discussed. So I get my compact form in this, where I get amplitude, frequency, phase angle all in one equation. Whereas in this equation, you see there is no phase angle appearing. So I want to have all these three descriptors of any harmonic motion, that is amplitude, frequency, and phase. I should have this form. So this form all can be obtained with the knowledge of our mathematics, trigonometry. That's what I explained you. So you would see in some other textbook, suddenly instead of a cos omega nt minus phi, you would see a sin omega nt plus phi. So here to differentiate, I just take it. You can assume instead of this, you can take this as like this, and then you have it happily. So you would see, you open a textbook or look at the literature, you would see these all functions here and there. So you have to get tuned to it. You should not worry. See, one book it is written like that, other book it is written like that. No, that kind of confusion should not come. That's why I'm making an attempt to explain you this. And this kind of discussion today would take you to the end of the lecture to understand what is state space representation. Clear? Do you get?
Yes, sir.
So this phi naught and a naught, I just introduced that other case. So this is case one solution you can consider. And this is another case two. So here I have my response by this function. Here I have my response by this function. But both are representing the same. Both whatever now we are drawing is representing the same what we have been discussing in the previous class. So what was the highlight crux of the previous class? The velocity, the displacement, velocity, acceleration vectors are rotating vectors in a harmonic motion, and they are differ by phase angle 5/2 respectively from displacement to velocity, from velocity to acceleration. That's what we have been seeing it. So that holds good in any of this form of equations that you consider, right? The intention of taking this kind of discussion is to have a clarity of showing you not to worry about looking at different textbooks, also to take you to space-phase representation, right? Is that clear? Shall I proceed?
Yes, sir.
Yeah. So now let me just summarize to you some of these points clearly, and then go ahead. So from this today, what we have learned, and we will march towards damped free vibration in the next class. So today's class, what we have learned is undamped free vibration. I'm repeatedly writing this again and again so that you should always distinguish them. Right, so undamped free vibration. So we are going to see damped free vibration. Then we are going to see undamped and damped forced vibration. So these are all kind of classification of vibration according to the state of start of your vibration motion. If it is by initial condition, some disturbance, it's free vibration. And if it is ever continue vibrating once the disturbance is given, that's undamped vibration. If it stops and the amplitude keeps reducing and then it stops at a point of time, then it is dampened, and that's called damped free vibration. If you have to execute a particular motion like a cam follower mechanism in an IC engine to operate your valves, so you have to rotate that. So there you see again this cam and follower mechanism. You see there a forced vibration may be required. So you have to give some forcing function. That forcing function can be of harmonic type or non-harmonic type and so on. So you start from this point, you have the branch, it keeps growing, right? I know there are students just after first year are there here, they have not gone through any vibration course. And that is the reason why I'm taking each and every step of them for them to get benefit. It is not that there's something they should know to understand this. This is the start of vibration that they can very well follow, and they would appreciate my effort and easy learning of yourself, right? So let's make some conclusion here. What are those conclusions? First conclusion, importantly, in harmonic exciter oscillators, you see that the natural frequency is given by root of k by m, where k, you know, is what is spring constant, and that can be obtained simply by to the spring attach a mass, and that spring would further elongate and stop at a point called static equilibrium position. When mass is not attached, it's at free length. When mass is attached, it is gone to static displacement. So if I have the static displacement, I can write now that W is what is equal to K into delta ST. So what the W is weight, which is mg here, that's equal to K delta ST at its static equilibrium position. It's free body diagram from the free body diagram. So K would be W by delta ST. So now the question is, how can you find out omega n in case you do not know stiffness and mass of the body under harmonic excitation? So it's a body is freely vibrating, but I do not know what is its mass and stiffness. But how can I get its natural frequency? It can be obtained from its free body diagram. That's what is that the second point conclusion. So I can write my omega n in terms of k by m, or in terms of see here it is going to be what, mg by delta st. So k by m is nothing but g by delta st. So I can replace in this expression g by delta st. So simply by looking at displacement from its amplitude of vibration, or the displacement, static displacement. I have that body which is vibrating. If I know that body, just it is and its free displacement delta st, if I know the deformation only if I know, then I would be able to get omega n simply from this. And we can also write, so this unit of this, you know, that is radians per second. That is circular frequency called, circular natural frequency called at this context. So you can always represent the frequency in cycles per second. So that would be simply 2 pi Fn is what is equal to omega n. So Fn would be omega n by 2 pi, and that's going to be in cycles per second, and otherwise called hertz. It's called a hertz. So if you know that, I can write now what is my natural frequency in terms of cycles per second. That's Fn is equal to 1 by 2 pi under root of g by delta st. So if that is so, I can also get time period of oscillation, that is Tn, that's equal to 1 by Fn, that's going to be equal to 2 pi under root of delta st by g. So without knowing the mass and stiffness of the body, if the body executes the motion simply by knowing if the body is acted upon by its force which is holding it, and the gravity, the displacement is what is going to tell you or to determine this. So this is how you can summarize, and this is an important point that you should remember while solving the problem, right? And then you see that the third aspect that I'm going to write is that responses, that whatever that we have seen. So x of t can be represented as a1 cos omega nt plus a2 sine omega nt. And we have seen that can be represented as a cos omega nt minus phi, or a naught sine omega nt plus phi naught, where here you know what is phi and phi naught. It's for the context only. So that comes from definition of a1 equals a cos phi, a2 as a sine phi, or a1 as a naught sine phi naught. I can take other way also. That's what I say. A2 as a naught cos phi. So what is that, you consider accordingly. And of course, you know here the summary that your A or A naught is not going to change, and that would be given by the root of x naught squared plus x dot naught by omega n xn, what is that we were writing?
By omega n square.
Yeah, so that's x naught omega n, x naught omega n, x naught omega n whole square. So this is a or a naught, and then you know what is phi and phi naught. So I just summarizing here. So phi would be tan inverse of a2 by a1. If I write a2 by a1, that's going to be x naught by x naught dot by x naught omega n. If I write in this case it is a1 by a2, then I will have tan inverse of x naught omega n by x naught dot. So this is point number 3.
Excuse me, sir.
Yeah.
Isn't it x naught by omega n? When a is equal to a naught is equal to x naught square plus x naught by omega n. X naught is not there in the denominator, right?
Yes, sir.
1 minute, 1 minute. Yeah, you're right. Yeah, that's what I was just trying to by heart and write it. That's right. We have written that as this, right? Because we got a2 as x naught by omega n. This velocity is always you remember velocity x naught dot is a omega n, a2 omega n. So that's correct. Thanks for telling here. Yeah. So far what we have written is clear, right? We confirmed. And now let's get into an interesting aspect of representing this motion. Let me just give you the summary from this. Just give me a minute. I have to use this. Let me just put this for you. Then look at these equations very carefully, right? Just a minute. Instead of drawing, I wanted to draw and show you like yesterday. Instead of that, let me just show you on this now. Someone is no unmuted. Please mute yourself. Already here outside, no, I get a road noise. I could find out who is not muted. Right? Manav, you want to go out of the class? Okay. So look at now here is what, are you able to see this diagram?
Yes, sir.
Yeah. So this graph I have put in here is to understand what are these equations that we look at it. So you can see that it is simply this equation here. This equation here. What is that? It is x of t equals a cos omega n t minus 5. A n t minus 5. Right? So see that how that is plotted. So yesterday doubt all would be clear. So you have here this vector A is displaced from vertical axis by omega t. So let me just zoom this further. So look at here. So this is omega t minus 5. So you see this a cos omega t minus 5. Omega nt minus 5 is the angular displacement of vector A from this, and this is an auxiliary circle for that. And then you see there is a phase angle phi. If I add, I'll get A1 from this. So this angle included by A and A1 is this. And you have this A1, A2. So the constants, whatever that you see A1, A2 are now is nothing but the components of this vector A. That's what we are writing A1 as A cos phi and A2 as A sin phi. And we have used it. So that is how this form we have got it here clearly, right? So now the variation of that, if you look at from the first peak, what is that angular displacement from origin is what is always representing the phase angle. That's what is 5 here. And from here, you could look at the cycle. And this is omega nt, so angular displacement is what is taken on this. So, and the amplitude is always maintained here is because it is not reducing is because undamped free vibration. And look at this graph here. It's function of t. It's function of t. Here it is function of angular displacement, and here it's function of time. In function of time, if you write, this phase angle should be divided by omega n. So 5 by omega n is what is this time. So you define here your time period of oscillation. And your amplitude is same as whatever that we have looked at now. So A equals under root of x naught square plus x naught dot by omega n whole square, right? So that's same, you have it here. So in this, you have to see that the tan phi, whatever that we define. So the tan phi value should be carefully looked at from the phase angle. If phase angle is an acute angle, you see that's positive. If phase angle is an obtuse angle, then you see that's negative. If phase angle is going beyond 180 degrees, then it is positive again. If phase angle is measured and it goes more than 270 degrees, 3 pi, in between 3 pi by 2 and 2 pi, then it is going to be again negative. So that's what does this vector diagram represent here. So on one axis you have what is that is called displacement. On the other axis, what is that is again it's a displacement, because it's see x naught dot by omega n. It's radians per second. It is meter per second. So it's going to be distance. So this is just going to be the ratios. So this is that just to understand, remember always what would be the value of your tan phi. Okay, so this is what is that you have to understand. Now, finally, we will look at another interesting representation of this. That's what I was telling you. How are you going to represent this in a plane called a phase plane or state space plane? So for that, let me again look at our known aspect. That is, what is that? X of t equals a cos omega nt plus phi, sorry, minus phi, right? Minus phi. Omega nt minus phi. This is what is our response. So let me write this now as cos omega nt minus phi as x by a, right? Just a minute, someone is unmuting and playing. I don't know who is that. Again, Mano. Mano, what is the problem for you? Do you have any doubts? Mano, Rohati?
No, sir. This time it was not Mano. It's on me.
Why
So
don't
I
you
typed
mute
by
yourself?
mistake.
Why don't you mute yourself?
Yes, sir. I muted. I muted.
Yeah, see, that's a kind of disturbance, man. This is highly, I told it's highly, complex and interesting aspect. You don't understand, please keep quiet. Otherwise, no, kind of disturbance, no, would take my thought process. So cos omega nt minus phi is equal to x by a. So here I can also write this x dot of t. So I have to represent what is representation in phase plane. Phase plane, or it's called the state space representation. So for that, I am just explaining you from what does that today we discuss the known aspect. So the response of free undamped free vibration is written in this way, and its amplitude value, its phi value, right? And now x dot of t is minus a omega n sine omega nt minus phi, right? So from this I can rewrite this for sine omega nt, sine, like I write for cos omega nt minus phi. Let me write now sine omega nt minus phi, and that's going to be x dot by minus x dot by a omega n. So let me write this as y by a, where y as minus x dot by omega n. This is y. So now you look at, I have x and y, represent x and y coordinate of xy plane. If I take xy plane, this is x plane and this is y plane. And I would have now representation of my motion in this way. So I have point A and point A here, and I can draw a circle through that. Just to draw the circle, right? This origin, this is a circle now, and this circle can be represented simply by this. So I have here cos term and sine term. So it is simply sine squared or cos squared omega nt minus phi plus sine squared omega nt minus phi would be what, equal to 1. So I would have here x squared by a square plus y squared by a square equals 1. So what is this equation? So this equation is a circle equation in xy plane of radius a. So I have this. This is a circle. And now I can also represent, what is, by the way, here, this y, the y is, we know that in this context it is x naught by omega n. X naught by omega n is taken here. So if I put instead of y, if I take my axis x and x and x dot. So x as a horizontal axis and x dot over here. So look at x is what is displacement, x dot is what is velocity. So if I have a plane represent x and velocity, displacement and velocity, or velocity now as function of displacement, if I represent, and that representation is what is called the state space representation. So what would happen now? What is my x dot? So I had y is equal to x dot by omega n. So now my x dot is going to be y omega n, y omega n, y omega n. What is my y? By the way, it is x dot by omega n. That's correct. So now, if this is going to be x dot, at this particular time, you know what is x dot also? It's y omega n in this, or it is in general, it has got its amplitude a times omega n. So this a amplitude times omega n is what is its velocity. But when I put here x dot, what is this axis going to be? Instead of having this radius a, this is going to be a times omega. So if omega happens to be less than 1, then it is going to be a minor axis, and this is going to be same as major axis a, and I would have this representation by an ellipse. So this is going to be here a omega n, and this is going to be a. So you have this kind of representation is what is called state space representation graphically. All right, so with that, let me stop today's class, and we will see again tomorrow the class with the again free vibration, but damped free vibration. I'm going to introduce what is damping into the mechanical vibration. So if you have any doubts now, please ask. Otherwise, we will end the lecture. If you do not have any doubts, I'll stop recording.